This work conducts LiDAR-IMU-Wheel Odometry, incorporating online calibration of a kinematic model for skid steering robots. To verify robustness of our online calibration, the robot's all-wheel radii are enlarged by 25%. To verify robustness to point cloud degeneracy, the narrow FOV LiDAR pointed at the wall only to imitate severe cases such as tunnels. The first experiment, point cloud degeneration and absence, are included as challenges. This video shows the result of trajectory estimation based on our odometry. We can see many point clouds are degenerated owing to the featureless environment. Point clouds were completely unavailable due to too close distance between the LiDAR and the wall. Our online calibration enables robust odometry estimation in point cloud degeneration and absence. In the second outdoor experiment, the robot moved on the glass, namely rough terrain, to verify our online uncertainty estimation. Unlike indoor flat terrains, the roll and pitch motions are not zero due to the roughness of the glass. Thus, we estimate the uncertainty of wheel odometry in 6 DOF and set this to the full linear wheel odometry factor. This is the result of the uncertainty estimation on the glass. The uncertainty for roll and pitch motions is huge due to the rough terrain, thus this estimation result is reasonable. This is a comparison result of the odometry estimation. We can see that our online uncertainty estimation and online calibration contribute to the odometry estimation accuracy. In the next experiment, the robot transited 3 terrain conditions. The first terrain is bricks. Next, the robot transited the outdoor stone tiles. In this area, the robot faced the first point cloud degeneration. Finally, the robot transited the indoor stone tiles. In this area, the robot faced long-term point cloud degeneration. FAST-LIO 2 failed due to short-term point cloud degeneration. Whereas, our method was the most accurate even in the long-term point cloud degeneration and terrain condition changes.